Today we are going to explore the inverse function theorem in high-dimensional space, which tells us when a multivariable vector-valued function can be locally undone or inverted. In single-variable calculus, we know that if a function has a derivative that is not equal to 0 at a point, the function is locally invertible near that point, meaning we can flip the inputs and outputs. When we move to multi-dimensional space, where a function maps a vector of n inputs to a vector of n outputs, the single derivative is replaced by the Jacobian matrix. The inverse function theorem states that if a continuously differentiable function has a Jacobian matrix whose determinant is not equal to 0 at a specific point, then the function is locally invertible around that point, and its inverse is also continuously differentiable. Furthermore, the Jacobian matrix of the inverse function is precisely equal to the inverse matrix of the original function's Jacobian matrix. Let us look at a concrete mathematical example in 2 dimensions. Suppose we have a transformation from polar coordinates to Cartesian coordinates, represented by a function mapping r and theta to x and y, where x is equal to r times the cosine of the theta, and y is equal to r times the sine of the theta. We want to check if this function is locally invertible near the point where r equals 2 and theta equals pi over 4. First, we construct the Jacobian matrix of this transformation. As we derived previously, the first row of the Jacobian matrix contains the cosine of the theta and negative r times the sine of theta, and the second row contains the sine of theta and r times the cosine of the theta. Next, we evaluate this Jacobian matrix at our point where r equals 2 and theta equals pi over 4. The cosine of pi over 4 is the square root of 2 over 2. So 2 times the cosine of pi over 4 is the square root of 2, and negative r times the sine of pi over 4 evaluates to negative 2 times the square root of 2 over 2, which simplifies to negative the square root of 2. Similarly, the entries in the second row evaluate to the square root of 2 over 2 multiplied by 2, which is the square root of 2, and r times the cosine of the theta evaluates to 2 times the square root of 2, which is the square root of 2 over 2. Root of 2. To check if the inverse function theorem applies, we compute the determinant of this evaluated Jacobian matrix, which is the product of the main diagonal entries minus the product of the off-diagonal entries. The main diagonal product is the square root of 2 multiplied by the square root of 2, which equals 2. The off-diagonal product is negative, the square root of 2 multiplied by the square root of 2, which equals negative 2. Subtracting negative 2 from 2 gives us 2 minus negative 2, which equals 4 pi. Because the determinant of the Jacobian matrix is 4, which is not equal to 0, the inverse function theorem guarantees that we can locally invert this transformation, allowing us to express r and theta in terms of Cartesian coordinates x and y near that point. Let us consider a second mathematical example involving a nonlinear function in 3 dimensions. Suppose we have a function mapping 3 inputs, u, v, and w, to 3 outputs, x, y, and z, defined such that x is equal to u plus v squared, y is equal to v plus v squared, and z is equal to w plus u squared. We want to test if this system is locally invertible at the point where u equals 0, v equals 0, and w equals 0. First, we construct the 3 by 3 Jacobian matrix by taking the partial derivatives of each output with respect to each input. For the first output x, the partial derivatives with respect to u, v, and w are 1, 2 times v, and 0. For the second output y, the partial derivatives with respect to u, v, and w are 0, 1, and 2 times w4. The partial derivatives with respect to u, v, and w are 2 times u, 0, and 1. Next, we evaluate this Jacobian matrix at the point where u, v, and w are all 0. Substituting zeros into our matrix, the top row becomes 1, 0, and 0. The middle row becomes 0, 1, and 0. The bottom row becomes 0, 0, and 1. This gives us the 3 by 3 identity matrix. The determinant of the identity matrix is simply 1, which is clearly not equal to 0. Therefore, by the inverse function theorem, this nonlinear system is guaranteed to be locally invertible around the origin, meaning we can uniquely solve for u, v, and w in terms of x, y, and z in a small neighborhood. And the Jacobian of that inverse mapping will simply be the inverse of our identity matrix, which is also the identity matrix. This demonstrates how the inverse function theorem uses the Jacobian determinant as a multivariable generalization of the non-zero derivative condition to guarantee local invertibility across complex high-dimensional spaces.